Why do we have another type of acid base so that we are not restricted to aqueous solutions? Bronsted-Lowry are really involving the transfer of an H plus ion from one substance to another. An acid is going to donate an H plus, and a base is going to accept an H plus. So I have two equations below. If you want it to be an acid, it must have an H atom that it can lose as an H plus. If you want to be a base, you have to have a non-bonding pair of electrons that can bind the H plus. So HCl is a Bronsted-Lowry acid. In the second equation, NH3 is a Bronsted-Lowry base. We have to have an acid with a base, so by default, water takes on those labels. So why is it that water can play either role? Why can it act as either a base or an acid? That's because water is an amphoteric substance. Things like HSO4 minus, HCO3 minus, there's many different ions and molecules that can capable of acting as either an acid or a base. With that comes the concept of a conjugate. They differ only in the presence or the absence of a proton. So as you look at these, if I add H plus to each of those initial species, I have now a conjugate acid-base pair. By definition, if a Bronsted-Lowry acid is a reactant, the product will be a conjugate base. We're going to be adding H plus. If the Bronsted-Lowry base is a reactant, the product will be a conjugate acid. We will be removing H plus. You have to practice with some real molecules because that's the only way to get a feel for these. So here's one more thing. If reactant water is a Bronsted-Lowry acid, the product will always be the conjugate base. If the reactant OH minus is a Bronsted-Lowry base, the product will always be the conjugate acid water. It all involves the transfer of a proton. So if I want to now apply this, if I want to find a conjugate base from an acid, what I will do is I will remove a proton. If I want to find the conjugate acid, what I will do is add a proton. Practice, that's the best thing I can say. Ammonia, it's easier sometimes to find those first because they have the lone pairs or the negative charge. That is your Bronsted-Lowry base, and you see it has a conjugate acid. Water by default is the Bronsted-Lowry acid, and its conjugate will be OH minus, the base. So it's a lot. What people did is they made a chart of the relative strength. You don't memorize this chart, you just use it when you're solving a problem. If we have a strong acid, you know that it will dissociate 100%. And so we say the base has negligible basicity. If we go down here to the bottom and we look at the strong bases, we know that they have negligible acidity. And in between are the weak acids, which are really the topic of this chapter, according to also some weak bases. It's a lot to, all right? So let's kind of look at a problem. How do we do this? Well, I just showed you that someone constructed a table of all the relative strengths. If you have a really strong acid, the base, the conjugate base, will be weaker. If you have a really strong base, the conjugate acid will be weaker. And equilibrium, we talked about that in chapter 15. It always favors a transfer of the proton from the stronger acid. Makes sense. It's kind of like the driving force for the reaction. So I've written a reaction there, phosphate ion plus water, and we make HPO4 2- and the hydroxide ion. Consider, who are the possible H plus donators? Well, can't be phosphate ion, has no hydrogens. Therefore, water has to be one of the donators, and by default, HPO4 2- must be a donator. When you look at the table, you will see that HPO4 2- is the stronger acid. It is above water. So I wrote It is above, water is below. So we always go from the stronger acid. That means the reverse reaction is favored. Equilibrium is going to lie to the left. So here I repeated it again. I put the little chart to the right. If someone gives you the full equation, there is the PO4 3 minus. Let's see if I can find it. I'm looking for the HPO4 2 minus and the water. Oh, they're sitting right next to each other. We see again that this is above, so we know that our equilibrium will lie to the left. But what if you're only given half an equation? What are you going to do? You look at the equation and you look for which is a stronger acid. We have HSO4 minus to consider, and we have H2S to consider. Find them on the chart and you will see that HSO4 is the stronger of the two. And what we will do is we will go to from the products SO4 2 minus aqueous and H2S aqueous. Have to spend some time here. It's a lot of trial and error and also thinking. To wrap up this chapter, I want it, not this chapter, this section. There are facts, okay? When I have what is termed a strong acid, it's going to completely transfer that H plus to water. That is just a fact. The conjugate bases, they will have a negligible tendency to be protonated. So if I have something like HCl, I know it will form H plus and Cl minus, and there is no reaction in the other direction. If I have a weak acid, they're only partially dissociated. We often write HA is H plus and A minus. We will be describing that more in the next video, but we know it's only partially dissociated. They're going to exist as a mixture of molecules and component ions. Most likely equilibrium is going to be lying to the left. So that's the difference really between a strong and a weak acid. The other fact is some materials will have no acidity whatsoever. They might contain an H, something like CH4, but they don't demonstrate any acidic behavior in water. If you make their conjugate base, if I say CH4 and we're going to take away a proton and we get the CH3 minus, that reaction will react completely. I should not have a double-headed arrow. I should just have a single arrow to regenerate the methane and produce a hydroxide ion. It's a tough section. Spend some time here, ask some questions.